off in the complex plane. They're nowhere near the real flux. So what we're replacing is, you take these two solutions, we're going to replace it by a contour integral around those solutions. This is not a contour deformation. It does not leave the value of the integral unchanged. In fact, what it's going to do is take us from the integral, which has dialogues and branch cuts and stuff like that. It's going to take us and give us a rational function which is very closely related to the coefficient. And the reason we're doing this somewhat obscure-looking operation, if I had simply started my lecture yesterday with this construction and said this is unitarity, then I think most of you would have wondered, what is this guy talking about? But I think you can see why this is essentially an operation of cutting and what the connection with unitarity is. So let's go back and do something useful with all this construction. Let's apply this cutting idea. So we have, if you can imagine, writing the amplitude in the abstract as the sum over Feynman diagrams and Feynman integrals. So we have these loop integrals on both sides of the equation. We start out with an object where we have an integral along the real slice, and on both sides of the equation, I want to make this replacement. I want to replace the contour along the real slice with a 4 torus encircling the global pole. So I want to apply quadruple cuts to both sides of that equation. So when we do the change of variables, when you do a parameterization of the loop momentum, of course, there's going to be a Jacobian there. That's going to live in the numerator. When we actually localize on the global pole, there's going to be another Jacobian in the denominator at one loop. Those turn out to be essentially constants in that it's just dependent on the external invariant, so we don't actually have to work them out in detail. On the left-hand side, we get a Jacobian, and that's going to be multiplied by a certain sum over the solutions of the equations, or equivalently, the global poles in our new language. And then, as usual, when we cut a line, we have to sum over all the intermediate states that can go in, so we have to sum over helicities. But now, it's not enough just to sum over helicities because we don't know the identity of the particle that can be circulating around the loop. So we also have to sum over the different kinds of species that can circulate in the loop. And we'll have a product when we isolate certain 4 selected propagators and we put them on shell. Well, what that does to get a product of 4 amplitudes, because these lines are now on shell and they're on their physical states. I'm just labeling these A, B, C, and D. Now, in this particular picture, I've drawn them as all being massive, but they don't have to be. They could be, for example, we could have leg C being massless. And then, what do we have here? We have our old friend, the 3-point amplitude. And everything is very nice because these momenta, remember our solutions are complex, so I've of course only shown you one of the loop momenta, but you can imagine when you shift that complex momentum by the external momenta which are real, then in fact all 4 of the cut loop momenta are going to be complex. So these 2 guys are complex, and everything is fine. We can find a non-vanishing value for our 3-point amplitude. So we can treat all the different boxes, whether the external legs are massive or massless, on the same footing. So we cut apart our loop amplitude into 4 free amplitudes, and we have to take the product of those things and sum over helicities and species, and that is going to give us the left-hand side of the equation. Now, on the right-hand side of the equation, there's a specific integral that's been picked out. Exactly which one depends on which global poles we've chosen. Different boxes will have different global poles, and of course, we're going to have to iterate over all of them in order to find all the coefficients. On the right-hand side, of course, we have the coefficient, because we care about global poles or anything. It's just a rational function sitting in front. And we have, of course, the same Jacobian. And we have nothing in the numerator, so we're just going to have 1. We should be evaluating 1. That numerator polynomial 1 is just 1. So we're going to be summing it, and that's just going to give us the number of solutions, which, as we've already seen, is 2. So we now have a useful equation because we can, of course, equate the left and the right-hand sides. And that gives us our equation for the box coefficient. And 1/2 from the number of solutions. We have to sum over the solutions to the quadruple quadruplet equation. We then sum over species and helicities of particles that can run around the loop. And we have the product of the 3 amplitudes running around the loop. formula is very nice. Because you'll notice, the first thing you'll notice is that there's no more algebraic reduction to be done. I'm not having to look at this coefficient and say, oh, there's the loop momentum dotted into some external leg. Let me break that apart into a sum of propagators and then cancel propagators. This is just it. This is just directly the coefficient. Moreover, something I didn't perhaps emphasize, but the scalar recursion relations, which you may have seen elsewhere, and the BCSW relations we saw, recursion relations we saw Monday, you can implement them purely numerically. So we have an explicit formula, which we saw for the spinor time. You can implement those numerically. That allows you to implement numerically the formula for A3. Out of A3, we can build any tree amplitude that we want, and we can do that purely numerically. You can run that recursion relation purely numerically. You program A3, and then you program the BCSW relationship, and you can run it purely numerically. And that means that this coefficient we can compute purely numerically. There's no need to do it analytically. It may produce a more efficient formula if you do it analytically and simplify it, but you don't have to. And that is, in fact, the way that these particular coefficients are computed in Black Hat, which is one of the codes that are available now, or one of the collaborations that uses the codes to do these next to leading order computations with high multiplicities of jets. So we've eliminated the last problem that we had earlier, and we've gotten this nice bonus that we have something that's suitable for direct numerical use. So we have, if you like, the beginnings of the numerical unitary forms. So before I go on, let me stop to see if there are any questions.
Yeah, sure. Further, when I compute some specific amplitude, how do I know what are the feed items or what the feed amplitudes are?
Very good. So let's imagine that you're trying to compute within the spirit of what we're talking about here. And in fact, we'll do some examples in a little while. But let's imagine you're trying to compute the one-loop corrections to a fixed gluon amplitude. Okay. Well, with 6 gluons, then I can't get any 4-mass boxes, and I can't get any 3-mass boxes either, so I just don't have enough external legs. So my list of boxes includes 1-mass boxes, easy, and hard 2-mass boxes. So, for example, I might have a box that has 1, 2, 3, 4, 5, 6, and I might have a box that has 1, 2, 3, 4, 5, and 6. And there are lots of other possibilities. You have to include all possible boxes that can actually show up. Okay, so in general, of course, I have to have amplitudes here, not just diagrams. So let me fill in all these corners. And now I'm going to apply the quadruple cut. Let me take this box as an example. So we're going to apply a quadruple cut. And what I'm instructed to do is to collect a list of all the tree amplitudes that appear going around this loop with all the different helicity configurations. I have some helicities for the external legs, but let me not worry about exactly what they are. Whatever they are, then I have to collect, for example, the positive and negative choices for helicity here, positive and negative choices for helicity here. We know that some of these vanish, and of course, if any one of these 4 amplitudes vanishes, you don't need to compute the rest. But some of these in general will be non-vanishing. And some of these you actually know how to write down without thinking about it, because in the 3-point case, of course, there isn't any sum of diagrams if we're starting from Lagrange. There's just a 3-point vertex. So I have to collect the various 4-point amplitudes with whatever the helicities of legs 4 and 5 are. So, for example, if you 4 plus the 5 minus, there's going to be 2 different amplitudes that we need over here. If both of these, for example, are negative helicity, there's only going to be 1 amplitude that we need to